For problem 3-24, there are givens your thermal conductivity and your H values, so you want to find the rate of heat transfer through the window and the inner surface temperature. You can assume steady state, one-dimensional heat transfer, there's constant K, and negligible radiation. So first solve, you can find the area by taking the length times width, which is both given. And then Ri is your just convection through the first area, so that's 1 over H1A. Plug in those values, you get a value. Your R glass, so L over Ka, same idea. Plug in value, you get a value. R's naught is R convect 2, same idea as R convect 1. And then R total is all of these added together. So then you can find your heat transfer, your rate of heat transfer through the window by taking the difference in temperatures, dividing by your R total, resistance total, and you get your answer here. Then to find T1, use your second transfer coefficient, so R convect 1, since you know each temperature on the side of that, you can find your temperature. Since you know one of the temperatures, you can find the other one based on the Q we got and the convection term. Next, for 3-73, we have some knowns, which are just your given values. We want to find the resistance of the wall and the heat transfer through the wall. So we can assume steady state one-dimensional heat transfer, constant thermal conductivity, and radiation is accounted for. So to find the total radiation, we add all of the total resistance, we add all of the resistances together. The first resistance is 1 over HIA. The middle resistances are L over Ka. You plug in the correct values for what portion of the wall you're looking at. And then R naught is 1 over H naught A. It's just the same thing as outside. So your R mid is your middle resistance. You can find that because it's in parallel. It's just 1 over R2 plus 1 over R3 to the negative 1. You get that value, add that to get all together, and you get 6.588 degrees C per watt. So then Q total is equal to your wattage times your area over your, or wattage times the dimensions over your area. So 406 watts for the entire wall. Next, 3-94. You know it's a 15 meter pipe DI, your inner diameter, your outer diameter. You want to find the rate of heat loss from the hot water and the velocity average of the pipe. So first you take the area of the inside and the outside. It's just pi r squared. I forgot to square. Pi times d times L, sorry. So then Ri is equal to 1 over HIAI, and then for the resistance of the pipe, that's ln of R2 over R1, 2 pi K1L, that's given. And then your radiation is your sigma times your epsilon times your temperatures. So then you get 5.167 watts per meter squared K. So your H combined is your H radiation plus your H convected since it's in series. You get this value. You can take R naught is equal to 1 over H combined A. You get that value. And then your R total is all of those added together. So you can take your heat transfer rate by taking your differences in temperature over your total resistance. You get 2928 watts. And then Q is equal to MC delta T. So you can find what your m dot is, your mass flow rate, and that's 0.2355 kilograms per second. Next, you can find your mass flow rate based on your density, which is 0.186 meters per second. Your Q dot for a portion of this is your differences in temperatures over Ri plus your R pipe. You plug that in, you get 77 degrees C. For 14-57, you know that you have diameters. There is a mass flow rate, and you want to find the total mass flow rate for the given one. So we can assume steady state one-dimensional no mass diffusion. So we can solve, you take your diffusion rate, which is your moles of diffusion over area. So then you can take your differences in concentration, which is given. So you get 1.14 times 10 to the negative 8 kilograms per meter squared times seconds. Your mass diffusion is equal to your big mass diffusion time, which is 2 kilograms times what we got here. And then if it's a 1.5 millimeter thick membrane, we change these dimensions and get 9.2 times 10 to the negative 8 kilograms per meter squared times seconds. Same process for the second part.